This video is the introduction video to Chapter 2, which talks about atoms, ions, and molecules. We talked in Chapter 1 about ionic compounds and molecular compounds, and here we are going to discuss the differences between those two, how to name them, so the nomenclature, and also we are going to take a look at the modern view of the atom. We're going to start by talking about three discoveries that were very influential in today's modern view of atomic structure. A man named J.J. Thomson used cathode ray tubes to generate beams of microscopic particles, which now are called electrons. So J.J. Thomson, whoops. So Thomson is cathode ray tubes, right? Cathode ray tubes equal electrons. Okay. Millikan, another scientist and discoverer, performed an experiment where he would place an electron on a drop of oil and levitate that drop of oil with a very large magnet. And based on the charge, right, on the magnetic plate, when he could get the drop of oil to levitate, he could actually determine the charge of the electron that was on the oil, because that was the only charge that was present. He would also know the mass of the oil, so he could calculate, or the oil drop, so he could derive the mass to charge ratio of an electron. So, Millikan, mass to charge ratio of electron. Right? Rutherford used gold foil and discovered that the atom had a very dense concentration of mass in the center, and basically discovered the nucleus with a positive charge. So, we're also going to talk really quickly about Dalton's atomic theory. Each element is composed of tiny indestructible particles called atoms. All atoms of an element are identical, and they are different from the atoms of another element. Atoms combined in simple ratios of whole numbers to form compounds, and atoms are not changed, created, or destroyed in chemical reactions. A reaction only changes the arrangement in which the atoms are bound. One of the main focuses of Chapter 2 is going to be on something called isotopes, and this video is mostly going to be focused on isotopes. Isotopes are different configurations of an element with differing number of neutrons. Remember, neutrons have the same mass, one atomic mass unit, as protons, but they have no charge, right? So increasing or decreasing the neutrons doesn't make the atom positively or negatively charged. That is for the electrons only to be doing. We use something called a mass spectrometer, which I won't really get into in this online course. You will definitely likely see a picture of a very generalized mass spec in a real in-person lecture course, but I just wanted to let you guys know that isotope abundance was determined by taking a random sample, passing it through a mass spectrometer, and determining how much of each that we have. So we can note an isotope in a couple different ways. Remember that I said an isotope, right, is an atom of an element with varying number of neutrons. Right? Neutrons. Sorry, the voice crack was funny. It happens to everyone. So you can choose to note these in a couple different ways. I've done neon for you. Okay? And, for this particular situation, if you're putting the atomic symbol in here, right, neon will always have 10 protons. If it doesn't have 10 protons, it's not neon. Okay? So when you're doing your isotope notations, there's no necessity to putting the atomic number in there, I'm more than fine if you just write the number of neutrons or the mass number, which is this A figure up here. So this A figure, right, don't worry about that Z. All right. So you got this table. Hopefully you have this table at least. And this is a bunch of practice problems. This is how you're going to see it on the test to identify different isotopes. I've done neon 20 for you, right? So I've listed the mass number with the element, so it's neon 20. It has 10 protons because neon is number 10 on the periodic table. It has 10 neutrons because the mass number, right, equals protons plus neutrons. Wow. Leave it to me to spell that wrong. Cool. So remember, mass number equals protons plus neutrons, right? And charge equals the protons plus the electrons. Remembering, right, that less electrons than protons means positive charge, and more electrons than protons means negative charge. Right? So let's do neon 22 together, right? We're told that it's neon 22. So we can write neon 22, right? It still has 10 protons because if it didn't have 10 protons, it wouldn't be neon. But instead of 10 neutrons, right, it has 22 minus 10, or 12 neutrons. Now since, and actually I'm going to rewrite this really quick. Right? So, since there's no charge on the neon, right, there's nothing written up here as a charge like there is on this silver, right? The electrons, number of electrons would just equal the number of protons, right? And the mass number, since we're told right here, is 22. Again, it's protons plus neutrons. I will let bromine 79, strontium 87, and this mystery be practice problems for you to do on your own. Try that yourself. When you're ready to check your answers, they're all down here. But try and do this before looking at the answers so you can be ready for the quiz, where you will have to do a number of questions just like this. We're going to do one more example from this table. That example being the silver 107 cation. Now, this is not a word that we have used before. Ions can either have a positive or a negative charge, right? And cation is what we call an ion with a positive charge, right? So cation, positively charged ion, right? So if it's a positively charged ion, right? If it's silver, it has to have 47 protons, right? If it didn't have 47 protons, it wouldn't be silver, right? Now, since it has 47 protons, right, we're just going to go straight across in the table. We're just going to do our mass number of 107, and we'll write that in right here, right, minus the 47. That gives us 60 neutrons. Now, here's the difficult part, right? And it's not as much difficult as it is just you have to get used to the fact that this is how you go about it, okay? The number of electrons is the only thing that changes in an ion, okay? It's the only thing that's different, okay? So remember how I said positively charged ions will have fewer electrons than they have protons, right? So they have more positive charge than they have negative charge, therefore their overall charge is positive. If we have a negatively charged ion, and I'll just write it right here, we call it an anion, right, as a negatively charged ion, that means there are more electrons than protons, so there's more negative charge than there is positive charge, so the overall charge is negative, right? Just taking 1 minute to look there. So if we have a +1 charge, that means we have one more proton than we have electrons. So under electrons, we can write 46. Feel free to do this next example by yourself as practice, following the methodology that I just went through. Okay? So I just threw in a couple isotopes of hydrogen that actually have their own names. Hydrogen-2 is actually known as deuterium, and hydrogen-3 is known as tritium. Deuterium actually comes in handy a lot in organic chemistry for neutral substitutions or heavier substitutions that don't show up on spectroscopy readings, such as infrared spectroscopy or proton NMR or 13C NMR. And you'll learn about that all in organic chemistry, so don't even worry about that. Right? Now, we have this thing called average atomic mass, right? And the atomic mass, right, so we just talked about all these isotopes. And chemicals and atoms and molecules and ions and all these fancy things, they exist in nature as isotopes, right? So even if the number of protons and neutrons are the same, it's still an isotope, right? And you see, if you look on the periodic table, just for an example, if you look at oxygen, you can see that it's listed at 15.999 grams per mole. Yeah, okay? And you're like, how did you get 15.999? And or why is it not 16? You can write 16. But it's 15.999 because of all the isotopes of oxygen that are out there, okay? We do a weighted average, so we accurately reflect the abundance of different isotopes, and we arrive at the average atomic mass, okay? But that being a weighted average, remember, it's not just adding them all up and dividing, right? We're accounting for the proportion at which they're found in nature. For another example, boron's average atomic mass is 10.81. It has two main isotopes, one that's about 10 grams per mole, one that's about 11 grams per mole. And you can tell, but since the average atomic mass is 10.81, the boron 11 is more abundant than the boron 10. Okay, right, because it's closer to 11, so the weighted average skews it that way. Okay. So, as it says in this last little button down here, and we'll do a practice problem with that, so fear not, we'll get there. The average atomic mass listed on the periodic table is the weighted average of the experimental masses of all the isotopes of that element. So basically, how abundant are they in nature, and that's how they're weighted on the periodic table. So, as promised, right, we will do two examples. The one example that we're going to do is the top one. The bottom one you can do for yourself as practice. So what is the average atomic mass of bromine, given that 50.54% is 79 Br and 49.46% is 81 Br? So if you cheat a little bit and you look at the periodic table, right, cheat a little bit, we see that it's about 79.9, or it's about 80 flat, right? This number is about 79, right? This number is about 81. They're about equal. It's basically clean cut between those two. Okay? This makes sense, but does the math actually work out? Well, we'll find out, right? Now remember, when we multiply when we multiply percents, we multiply the percent as a decimal, right? So we can start with the first number. So 78.9183 AMUs times 50.54%, or 0.5054. Remember, just dividing by 100 converts that back. Plus, right, 80.9163 AMUs times 49.46%, or 0.4946. Right. So, remember, we're multiplying as a decimal. We can't have over 100% or more than we had at the start, right? So, when you multiply these together, you do, in fact, get 79.904. Which is what you see on the periodic table. Go ahead and do the boron example yourself. Try that out. It should come up to the number that, or very close to the number that is on the periodic table. Okay, so this is how you're going to check yourself for that question. Okay. So, now that we're in to the periodic table, let's continue about the periodic table and talk about what these areas are called. So the periodic table is split up into periods and groups. The groups are the columns, the periods are the rows. Okay. So if you're in group 1, that leftmost group coming down, hydrogen, lithium, sodium, potassium, rubidium, cesium, francium, we call those the alkali metals. If you're in group 2, beryllium, magnesium, calcium, etc., we call you the alkaline, spelled differently. Earth metals. If you're in group 17, we call you the halogens. And if you're in group 18, this one you probably heard before, you are the noble gases. Or the inert gases. Why? Because they don't react. They play nicely with everyone on the playground. Okay, so a couple other names that you should know. Right? Groups 3 through 12 are called the transition metals. Right? Groups 1 and 2, 13 through 18, right? We're actually going to skip this one real quick. We're going to come back to that. Right? The bottom 2 rows are called the rare earth metals. Right? Take a moment. Make sure you have all those written down. Make sure they're spelled correctly. And take about 30 seconds and just find them on the periodic table so you kind of can equate to where they are. So now that you've done that and looked at the periodic table, now we can move on. We're just going to leave this out. Again, just for the purposes of this specific video, we'll leave that out. That can be covered in a later topic later or in person. So now we're actually into compounds. So that is the end of this video. Again, we spent our time talking today about isotopes and common ways that elements and atoms exist in the real world. See you in the next chapter 2 video. Remember to do this practice problem.